Slow 4. 1, 2, 3, 4.
Bless the Father, bless the Son, cross your heart, 'cause you're the one collecting moonbeams in the morning. Curvy sticks and wooden poles assisting you in plugging holes. Plug them holes till you see straight through to the mind's eye. Think about it, turn around and go back to the quiet sound of Jim and Dan prancing around the pool. You were the fool.
We can go now because once we finished all algorithms on Thursday, we'll go ahead and start on the last module, which is trees, and then tree and tree-based data structures, that is. So remember last time we were looking at ways of proving big O analysis, that if you've got two functions, f and g, how do you prove that f is big O of g? Well, first of all, you need to write out your intuition, and that's usually going to be pretty easy, right? Because you'll have a good sense that one of these functions is bigger than the other in the limit, right? The first technique that we covered was finding a crossover point, right? And that means finding roots. And essentially what you're doing is you're fixing the c in the definition, where f of n is bounded above by c of g of n for all n greater than or equal to n naught, and then you're finding this n naught. So you fix c to be 1, which means f is less than or equal to g after that certain point. That means you're finding those crossover points, right? And if you were to plot this, these are the two that we were playing with last time, plot 175 n squared plus n, and then n cubed, right? If you only looked at it from 0 to 100, you would get the misimpression that n cubed is better because that's on the bottom, right? Lower is better because less time, less memory, less resources. But if you zoomed out here over to 200, right, then you would see that at some point they cross over. There's your n naught. For every integer after that, that other function will be greater than the blue function there, that n squared function, right? And that works as long as you're finding roots works, right? And that example was artificial to find roots easily using the quadratic equation, along with a root that was trivial, 0, right? Technique B was to simply set up an inequality to make your function bigger and bigger until it matches, right? Now what that means is if you're going to take this function and you're going to make it bigger and bigger and bigger until it matches this, you're going to make it look something like this. Say it's 2 times n cubed, right? Now if I increase that function, then what I've done is instead of fixing c, I've fixed n naught, or I've fixed n naught to be 0. And I want to push this crossover point, this intersection, back. That's what I've done with this green function here, right? Now the intersection point is back over here. But multiplying a function, right, by a scalar does not change its rate of growth, because the first derivative of a scalar, like 2, is 0. And there's no rate of growth change there at all, right? So if I can push it back by twice as much, there's nothing to stop me from pushing it back by thrice as much, right? And let's go ahead and zoom in from 0 to 100 and see where it's intersecting now. There's that pushback point for 2. There's the pushback point for 3, right? And I'm just going to keep pushing it back and pushing it back until it's big enough. Well, just make it 300 then, right? Now certainly that's been pushed all the way back to 0, right? So all you need to do is make it bigger and bigger and bigger until it matches. And we did that exercise with these 2 examples here, right? What I want to do now is do a few more examples with some other functions, right? All right, so for example, let's suppose that f of n is 2.5n, right? And g of n is n, right? Now, what's your intuition here? Which one of these is bigger? Right? They're both linear, right? So neither one is. I could prove that f of n is big O of g of n, or I could prove that g of n is big O of f of n, because they're both true. Let me go ahead and show that f of n, however, is big O of g of n. Right? All you have to do is set up your inequality. 2.5n is less than or equal to I want to make this eventually look like less than or equal to c g of n. In other words, some c times n. Well, guess what? I'm already there. 2.5 n. So for c being 2.5 and n naught being 0, the inequality holds. Right? So that's just to get us warmed up here, right? That it doesn't matter what the constants out front are, because you can always take the constants over to the right-hand side and you're done with your proof, okay? Here's another one. So if it involves polynomials, it's pretty straightforward. But what happens when it does not involve polynomials? What if I've got f of n is n log of 64n, and then g of n is n log n. Now, both of these are what are called quasi-linear. We'll talk about that in a second here. But there's n, and there's a log n, and there's an n and another log n. There's just this really annoying constant sitting here. How do we take care of that? So first of all, I'm going to state that f of n is big O of g of n, and here's my proof. Right? I'm going to set up an inequality. N log n, or log 64n, excuse me, right? I want to show that that's eventually less than or equal to c times n log n. Right? Now remember, what are my logs base? Implicitly it's base 2, because we're all computer scientists, right? All right, so what do I do about this? How can I get rid of that 64? If I've got a logarithm and a times b, what can you do with that? You could change it to the natural log, but we're always going to work in base 2, right? But the same identities that apply to natural log apply to any log base. So if I've got a log with a product inside of it, I can split that up into a addition. Log base 2 of 64 plus log base 2 implicit of n, right? So you just have to remember your log identities from high school or algebra, or whenever they introduce those things, right? Tell me about that log base 2 of 64. So what power do you need to raise 2 to get 64? Because that's what the logs do, right? That's going to be 6, right? Plus log n. Now I'm just going to go ahead and do some algebra and rearrange things. And what do I have? I have n log n plus 6n. Okay? That's looking kind of like this. I've got it now. I've got that one, the first term in that form, but I don't have the second term in this form yet. That's okay. You can make it bigger, right? Let's go ahead and erase this stuff here. Right? This is less than or equal to n log n. That's the first term. It doesn't change. Plus 6n log n, right? Because log is a monotone increasing function. Be careful. Is this true for all n greater than or equal to 0? So is this less than or equal to this for all n greater than or equal to 0? Well, certainly 0 will 0 out. What happens if you try to take a log of 0, though? It's undefined, right? It technically, I mean, if you want to take the limit, it goes down to negative infinity. But algebraically, it's undefined, right? Can't do that, all right? So no, that's not true. Is it greater than, or is it true for n greater than or equal to 1? Right? Well, what happens with 1 here? What's the log of 1 now? Any base? 0, right? So this ends up being 1 times 0, right? And then this ends up being 1. So this entire thing becomes 6, right? This becomes 0. This becomes 0. Is 6 less than or equal to 0? No. All right, so is this not true at all? No, we just need to go one more. What values is it true for? For all n greater than or equal to 2. And so this is why you need to be careful with your n naught, right? That after some point it's well defined and the inequality holds here. Right? So this is true for all n greater than or equal to 2, for n greater than equal to 2. Now we've got it into the form that we want, because the first one is 6 times the second one, or the second one is 6 times the first one. So altogether this is 7n log n, right? And for C being 7 and n naught being 2, the inequality holds, right? You just have to make sure that your chain of reasoning here, that your chain of proofs are correct for whatever values you're talking about. If you told me that this is true for all n greater than or equal to 0, that's definitely not true, right? It's not true for 0, and it's not true for 1. Okay? All right. Another example. We've seen ones involving logarithms. We've seen ones involving polynomials. What about ones involving exponential functions? For example, what if I had n times 2 to the n, and then g is equal to 3 to the n, right? Which one of these do you think is bigger in the limit, first of all? Yes, there is a linear term over here. If that were not here, would you have a clear intuition about which one is bigger? Right. Bigger bases mean bigger functions. Does this wash out that? Absolutely not, right? So my intuition tells me that f of n is big O of g of n, okay? Now we need to set up the inequality. N times 2 to the n is less than or equal to, right, dot, dot, dot. We want to make this look like c times g of n, which is 3 to the n, right? How do we do that? Well, I've got two terms here. I've actually got two sub-functions, f1, which is going to be the linear term, and f2, which is the exponential term. And so the entire function here is f1 times f2. I want to collapse that down so that I'm only dealing with one term, right? One way of doing that, one naive way of doing that, would be to say, well, this is certainly true, right? Because n is less than or equal to 2 to the n for all n greater than or equal to 0. First of all, verify that that's true. 0, 0. Right? This becomes 1. That's right. What if it's 1? 1, that's right. 2, 2, and now it's growing bigger. Right? This would actually require, formally this would require a proof by induction, but we're in obvious land right here. Right? As long as your obvious land excludes those corner cases where it's not defined or it ends up being wrong, incorrect, right? All right, well, what does that equal to? So I've got a common exponent, so it'd be 2 times 2 to the n, which would be 4 to the n. Uh-oh. I've exceeded what I wanted to show. This is certainly true. It's certainly true that a billion is greater than 1, right? But I've gone way too big here. Right? So nope, I'm going to have to back this up. You can make it bigger and bigger and bigger, but you can't make it too big because you might overjump or surpass what you're trying to show. This is why I like writing the proofs out like this and then keeping an eye out for what you want to show, because then you know, oh no, I've already become bigger than that. Right? All right. Another naive way that you might do this is 2 times 2 to the n. Right? First of all, is that true? No. Is n less than or equal to 2 for all? Or here, I don't know if you know that. For all, that's that symbol. For all, if you've ever seen this. For all. There we go. N greater than or equal to 0. No. Is it true for 4? Absolutely not. Right? So you can get rid of terms, but you have to make them bigger. Right? Well, I could do n squared instead, but that really doesn't help me. Right? I want to get it in a form here that will end up when I multiply them together, will give me 3 to the n. What will do that? Remember, bases with a common exponent are equal to ab raised to the n. So if one of these is 2, how do I get this to equal to 3? 1. 0.5 to the n, right? Because if it's actually 1 to the n, then it never changes. It's always just 1, 1, 1, 1, 1, 1, right? There we go. All right. And verify that that's true for all n greater than or equal to 0. That is true, right? And that's equal to 3 to the n. So for n not being 0 and c being 1, the inequality holds, and we're good. All right. Well, we've seen them now with polynomials, logarithms, exponentials. What happens when we have a combination thereof, right? For example, f of n is equal to log of, how do you read that? N with an exclamation point. What is that called? That's a factorial function. Or more formally, it's the gamma function, right? Right? And I want to show that this is n log n, right? Or actually, what's our intuition here? N factorial is huge, right? So does that mean if you take the log of n factorial that it's still huge? Now, when you take the log of something, it diminishes it so much that it might become manageable, like n log n, right? So my intuition here, in fact, these have the same exact, you could show either way. F of n is big O of g of n, or vice versa, because it's true. But I'm going to show the easy way. I'm going to show that f of n is big O of g of n. Okay? Again, let's set up the inequality. Log of n factorial. Okay? What is that equal to, first of all? Well, the definition of log is n times n minus 1 times n minus 2 times ... 3 times 2 times 1. Okay? Now, remember, I'm trying to make this bigger. I'm trying to make it bigger and bigger and bigger until it looks like this guy right here. Okay? What is the largest term in this product right here? It's n, right? So I could make it bigger by changing the second one to n, because n is greater than n minus 1, right? I could do the same thing for the third term. I could do the same thing for the fourth term, et cetera, et cetera, et cetera. I could change them all into n's, ... n times n times n. Now, how many n's are there in there? N of them. There are n n's here. So that's equal to log of what? N to the power of n. Right? Now, once again, what are your logarithmic identities? If you've got a to the k, right? What can you do to that k? Bring it out front. So that's equal to n log n. Right? Hey, that looks like that. So for c being 1, and be careful, n not being what? Is n not being 0 well defined? 0 factorial is what? Well, careful. It's actually technically 1. Right? The number of ways of this measures arrangements, right? So how many ways are there of arranging one person? 1 factorial, 1. How many ways are there arranging 2 people? This way or that way, right? And so it's 2. But how many ways are there of arranging 0 people? 1, because you don't do anything, right? It's vacuous, right? All right, so that means that this is well defined, right? This is log of 1, then this is going to be 0. So this ends up being 0 on the right-hand side. But what about n log n when it's 0, right? 0 times log of 0. Is that well defined? No. So we're going to say at least 1. Right? Now be careful. This is 1, and so this is 0 on the left-hand side. This is 1, 1, so this is 0, ends at 0 on the right-hand side, so we're still good. Right? You got to verify those corner cases right there, or provide a full proof by induction or something. Okay? All right. If you want to, we can go ahead and just, make up any functions that we want to and then try them out or something like that. But instead, let's go ahead and review some of the categories that we've already seen. Oh, and by the way, I don't assume calculus here, but you can do calculus too. There's a third technique. You set up a limit. Did we talk about that on Thursday, I think? Did we? If not, again, it requires some calculus. Some limits are obvious. If the numerator or denominator are growing, but the other is not, then it's obvious. It may require some, like L'Hopital's law or something like that. But in any case, we're not going to do that. Right? Instead, let's consider categories of functions. Categories of functions. Right? Of complexity functions. So I'll just go ahead and start us out here. Constant, right? Order 1, right? You would typically see that if you're just doing some, like you're doing 5 multiplications and 7 subtractions or something, right? A formula computation. Right? If you just plug and chug into a formula in a computer, like the quadratic equation or something like that, there are a fixed number of operations. It doesn't depend on the input size, right? And so formula computations. What would be larger than that, though? Give me a type of function that's larger. You know what? We're going to die here in a second if we don't plug in. Let me go ahead and take a pause and actually plug in. All right, linear. I like that. Right? It's going to be order n. Okay? Where have we seen examples of that, by the way? It's in the name. Linear search. Right? Pretty much any algorithm that you've written up to this point where you've had to iterate over an array or a list or a set, right? You end up processing everything inside that set. It's all going to be linear, right? There's something actually sandwiched in between those, though. Something that's more than constant but less than linear. Logarithmic, right? In other words, order of log of n. There we go. Where have we seen that? Remember that really fast search? Requires it to be sorted first, of course, and then you can exploit that ordering. Binary search, right? Okay. Now going above linear, what else do we have? What's next? You could go exponential. But there's plenty of stuff in between that, though. Quadratic, right? Quadratic would be order n squared. And we've seen that before with, say, insertion sort, selection sort. And, of course, what started us all out over here. If we go back and take a look at that linked list implementation where we naively use this get operation, it ends up being n squared. Consequently, for an input size of 1 billion, right, there's an estimate of taking 20 years. Right? So naive linked list iterations. Right? Iteration. There's another example. Actually, before we go on to the bigger ones, there's something sandwiched between linear and quadratic, and it's called quasi-linear. Right? And this is going to be order n log n. And this is going to come up today when we start looking at some other algorithms here. For example, merge sort, and quick sort. But that's kind of the holy grail of algorithms right there. Because as we've already seen, if you go up to quadratic, you're already cooked. Right? Yeah, it's going to take you 20 years to do 1 billion elements. Right? Linear, we've seen. Well, okay, well, that's going to take it's a mere 3 seconds instead of 20 years, right? But some things are going to require searching and sorting, and this is the best that you can do. N log n. We call it quasi-linear. Quasi means almost, right? So it's almost linear. It would be linear if it weren't for this annoying little log factor over here. But remember, logs grow so small. If you take the first derivative of log, it's 1 over n. So the growth rate is actually diminishing. That we can probably just ignore that logarithmic term, right, for all practical purposes. Right? We would have to get up to orders of magnitude larger than the universe for this to start mattering that much. This logarithmic term to matter. Right? That linear term is going to dominate. Okay. All right. So before that, though, before quadratic, you also have cubic And then you can generalize that to any polynomial, quartic, right, quintic, or what. And we generally stop giving them names after that point because they're not too common. But cubic does come up with, say, matrix operations, say multiplication, right, or graph algorithms. So you'll see that a lot. However, if you really take a closer look at a lot of those, they're not cubic. They're just slightly less than quadratic, because the fact is that the input is already cubic, right? Or the input is already quadratic. If you have an n by n matrix, what is the input size? N squared, right? And so you can't really say that it's n cubed with respect to the input size, because the input size is a little bit different. However, theoretically, if you come up with something like a polynomial, one that I can think of off the top of my head is, remember we looked at primality testing as an example, right? That we just continuously try to divide by an integer until we find a divisor, and we say that it's not prime, or we try all the divisors and say that it is prime. There's something called the AKS algorithm, which is actually n to the 12th, right? It's very, very unnatural because it uses advanced mathematics, and so the best that they came up with was n to the 12th. So we could say, oh, it's a polynomial time, but there's no way that it's feasible, right, for any reasonable input. Exponential, of course, would be order 2 to the n, right, or any k to the n, right? Not all exponentials are created equal. That is, I can say that 2 to the n is big O of 3 to the n. Oops, parenthesis right there. But it is not the case that 3 to the n is not equal to order 2 to the n. There we go. So if you have a base even slightly larger, right, then you are in a completely different complexity class here. Yes, we call all of these things exponential, but 2 to the n and 3 to the n are not the same. 3 to the n is much larger, right? As we already just proved, actually. You can go beyond that. Remember that factorial guy there? That would be called super exponential, right? That's going to be any exponential, because as we've seen, one estimate that you can use is n to the n, right? And now both the base and the exponent are growing together, right? And then, of course, anything beyond that is also super exponential, right? But we've already seen that anything quadratic and above is not at all acceptable in computing, in real computing, in practical computing. You're talking about, if you get up to the super exponential, you're talking about more atoms in the universe. You couldn't even build a computer that large to hold all of that data, right? Much less process it within the lifetime of the universe, right? For example, if you wanted to analyze all possible card shuffles of a 52 card deck, right? 52 factorial, it ain't happening, right? That you are going to wait until the heat death of the universe to be able to compute something like that, right? So, for all practical purposes, you're really only going to want to look at algorithms that are constant, logarithmic, linear, or quasi-linear, right? Okay? All right, well, what do we do about some algorithms that you might have seen before that are, say, recursive? So did you cover recursion in CS1? Yes? No? Oh, no? Not at all? Okay. All right, well, let's take an aside really quick here. You've all seen the Fibonacci sequence, right? So here's a sequence of numbers. 1, 1. I'll start it out as 1, 1. 2, 3, 5, 8. Now, what's the pattern that I'm following here? The next value here, the next value here is going to be the sum of the two previous values. So 13, what's the next value? 21, right? And et cetera, it goes on forever here. This is a recursive sequence, right? F of n is equal to the previous value in the sequence, f of n minus 1, plus f of n minus 2, right? And you can solve this and come up with a closed form solution of it, but let's go ahead and code it instead. Right? Here we go. get rid of this. All goes, all right. Yeah, let's go ahead and go with just what we have right here, demo really quick. All right. No, let's go ahead and go with the new one, I guess. I don't want to get rid of that. Fib. There we go. All right, so let's create a function to compute the Fibonacci number. Public int fib, and we'll take int n here, okay? Now, when you write recursive code, you look at the base case. You need two starting points here, right? Because this is in terms of two previous values here. So if n is equal to 0, or if n is equal to 1, then we return 1, because those first two values are 1 and 1, okay? Otherwise, we return what? F of n minus 1 and add f of n minus 2, or f of n minus 2. Well, don't we have a function to compute that? This function. So, fib of n minus 1 and fib of n minus 2. There's recursion in a nutshell, right? That you have a function that calls itself, right? One or more times in this case, right? Does this look familiar now? Okay, so recursion is simply just a function calling itself, okay? It comes up in many divide and conquer style algorithms. So before we get to the analysis, let's look at one example called merge sort. Right? Now merge sort takes a divide and conquer approach. Let me go ahead and give you some values here. 7, 3, 4, 8, 1, 5, 6, and 2. Right? Now if this were an array, if I started out as this as an array, what it does is it tries to divide and conquer it. So it's going to divide it in half. Right? And then it's going to split it up into two inputs, 7, 3, 4, and 8, and 1, 5, 6, and 2. And I won't draw it fancy anymore here to save time. All right, well, I still don't know how to sort this stuff, so I'm going to divide it again. Right? I'm going to divide this into 7 and 3, and 4 and 8. I'm going to divide this into 1 and 5, and 6 and 2. I still don't know how to sort this. So what I'm going to do is I'm going to split this up even further. 7 and 3, 4 and 8, 1 and 5, and 6 and 2. Now, I'm only dealing with a single number. Do you know how to sort that now? If I only have one number, it's, by definition, it's sorted. Right? So, I divide it down until I have a trivial solution, one element. Then once I've got sub-solutions, I need to start combining them again. I'm dividing and I'm conquering. So now I'm in the conquer phase. What I need to do is merge these. And what I'm going to do is I'm going to jump forward in the algorithm here. 3, 4, 7, and 8. 3, 4, 7, and 8. Suppose I had that as a subarray. And then I have the other subarray here that's already been sorted. 1, 2, 5, and 6. 1, 2, 5, and 6. What I need to do now is I need to merge them together, giving you merge sort. Right? The way that I'm going to do that, let me give myself some more room by moving this down. Right? I'm going to keep track of two index values here, I and j, and then actually a third index value, right, called k. Right? Now, what is the process for merging these together? I'm going to look at the value. This is the left or right, and then this one is the right one. Right? I'm going to look at the L sub I and R sub j here. In other words, 1 and 3. Which one of these would go first into the resulting array? The least one. So I'm going to go ahead and copy this over, right? 1. And then I'm going to advance my pointer here, my index reference, to the next element. Also k, I'm going to advance that to the next one as well. In fact, let me put it down here, right, so that it's out of the way. There's k. Right? And so I'm going to advance that to the next
spot here. Okay? I proceed exactly as I just did, right? 1, 2, okay, so now 2 and 3. Which one gets copied over? 2 now gets copied over, right? 2. And once again, I advance my j, and I advance my k. At this point, I'm looking at 5 and 3. 3 now gets copied over. And when I do that, I advance my k, and I advance my I this time, right? And so I continue in this manner. 4 gets copied over, right? And I advance k, and I advance I. Right? 5 versus 7, that gets 5 gets copied over. And now at this point, I'm going to go ahead and fast forward 5, 6, 7, and 8. I have merged 2 sets together, 2 sets of arrays. Okay. So there's a divide phase where I divide it down until it's just a trivial solution. You don't have to sort something of size 1, right? And then I start merging it back together in using this process here. Okay? All right. So let's take a look at the pseudocode because it's recursive. Merge sort right there. Right? Zoom in a little bit here. There's an input that's a subcollection of A, L through AR. Initially, it'll be 1 to N when I first call this thing. Okay? Then we're going to output a sorted version of that. This is going to look a lot, all of this is going to look very familiar because it's the same divide and conquer strategy as, say, binary search, right? So if L has not exceeded R, that means that we've got an array of at least one element, right? Or, yeah, well, at least 2 elements, excuse me. Because once it's equal to, then it's of size 1, and we don't do anything except return that one element. Sometimes it could be 0, right? So if L is greater than R, that means that the array is empty now, right? Just like binary search, that's when you stop and you quit, right? That L and R have now exceeded each other, and you're not looking at a valid array anymore. We compute the middle index here, which is just the average of L and R, right? And then we split it up from L to M and M plus 1 to R. Right? So here's your original array, going from L to R, and then M gets computed as the middle index there, M plus 1. So you get a cut right here. This goes to one recursive call, and the right-hand side goes to one recursive call. That is these recursive calls right here. Merge sort on the left and merge sort on the right. Remember, once it's done sorting, it will return it here, right? Or it'll return it right here. Right? So what is this merge routine here? That's a non-recursive version. That's a non-recursive subroutine. Let's take a look at what that looks like. Merge right there. Right? It's a little bit more complicated, but it's basically what I just walked you through. Given 2 sorted collections, left and right, of sizes n and m respectively, we are going to merge them together into A. Right? So I'll create A, which is a new empty collection of size n plus m to hold everything. I have my I index and my j index, which is a variable for L and R respectively. I've got my k index, which is a variable for A. Then, while I has not fallen off the edge of the left one, and j has not fallen off the edge of the right one, if L is less than R, then I copy over L. Otherwise, I copy over R. And then I advance I or j, depending on which one I did. Then I advance k because I copied it over to A, and so I'm always moving that k over. Right? At this point, at least one of the collections is empty, so we blindly copy the other one, right? Because either I has fallen off of L or j has fallen off of R. Right? So let's go ahead and copy over the rest in L and or the rest in, it's exclusive or actually, the rest in R here. Advancing I, advancing j, advancing k in either case. All right? And we output that value. Okay? There's no recursion here at all. This is just a iterative subroutine, okay? So this is a basic divide and conquer strategy, and it's usually presented as a recursive algorithm, okay? Now that we've got that as a review here, how do we actually go about analyzing this thing, right? So, actually, let's review, I guess let's review merge sort here first, right? The notes that I've got, right? Yeah, here we go. We'll come back to this as well. We need to ensure a good equal split in the collection by breaking it up into two parts first, until you have a sub-collection of size at most 1. It could be 0, because if you have 7 elements there, you end up breaking it up into 3 and 4. 3 gets broken up into 1 and 2, and then 1 gets broken up into 0 and 1, right? But you could have an empty array, right? As you return from the recursion, you merge the two sorted arrays together, right? That's how it works. So how do we go about analyzing this thing? Well, first of all, you have to define a recursion. A recursion like the Fibonacci sequence, right? Where you set up a function that is in terms of itself, right? You define a recursive function that captures the idea of work with respect to the elementary operation. Then you set up the recursion, right? You capture the notion of recursive work. How many calls to the function do you make, and how big is the input size for each call? Right? Then you solve the recursion, right? And even in your, I forget what number you told me it was, but the discrete math course from IS&T, have you done solving linear homogeneous recurrence relations of degree 2 or 3 or anything? No? All right, good. We won't solve them either, right? Instead, I'll give you a tool to solve, and not even solve them, but it's something called the master theorem. Right? But what I want to do first is I want to analyze this algorithm, right? Okay? All right, to do that, we need to follow those 3 steps. We're going to set up a recursion here, C sub n. It's a function. And it's going to be the number of comparisons by merge sort on an input of size n. Okay? All I need to do is get a handle on C sub n here. Okay? So let's start at the top. Well, if the size is 0, we don't do any work. We just simply output it. Okay? Otherwise, we do an addition, we do a division, we do an assignment, right? But ... Here's where there's one call. Right? Here's another call. We call it on the left half and the right half. Right? So there are going to be 2 function calls here. This is equal to C sub something plus C sub something else. This is going to be the left recursion. And this one is going to be the right recursion. Okay? Now, what is the input size to each one of those calls? If the input size was originally n here, and we cut it in half and recursed on the left half, and then cut it in half and recursed on the right half, how big is each one of these? N divided by 2. And this one is n divided by 2. So let's update our values here. N divided by 2, n divided by 2. Granted, it could be off by 1 because 7 divided by 2 is either 3 or 4, right? We're going to ignore that, right? Okay? Now be careful because you're also doing work here, right? So that took care of this recursive call, that took care of this recursive call, but you're actually doing work in this other subroutine too. So let's focus on that now. What is the elementary operation again? It's the number of comparisons, okay? I see a comparison here and here, but remember, those are necessary for the control structure of the algorithm, right? That controls the while loop, right? That's not actually a comparison. You were talking about comparisons of things inside the array, right there, right? Do we actually do any comparisons here? Well, we do right here, but again, it's necessary for the control structure of the while loop. Necessary for the control structure of the while loop. We actually don't do any here and here. So as an aside here, what is the best case scenario? Best case. The best case scenario is when I have, say, 1, 2, 3, 4, 5, 6, 7, 8 as my two subarrays, right? How many comparisons will I end up making? I will compare 1 and 5 to realize that I need to copy over 1. Then I'll advance over here to 2, and I'll compare 2 to 5 to see that I need to copy over 2. 3 to 5 to copy over 3. 4 to 5 to copy over 5. Oh, sorry, copy over 4, right? But at that point, this one has been emptied out. I have now jumped out of this main while loop where I'm doing my one elementary operation, and either this while loop, everything will be copied over blindly, or this thing, everything will be copied over blindly. Right? So in terms of n, right? Here's n elements here. How many is, say that there's n divided by 2 over here and n divided by 2 over here for a total of n elements. In the best case scenario here, at most, how many comparisons do I have to make? N over 2. Right? That's the best case scenario. Right? What's the worst case scenario? Worst case. I'll give you the setup here, and then we'll do it together. 2, 4, 6, and 8. Can you predict what's going to happen here with 1, 3, 5, 7, and 2, 4, 6, 8? Right? I'm going to have to compare 1 and 2 to copy over 1. Then I will compare 2 and 3 to copy over 2. Then I'll compare 3 and 4 to copy over 3. 5 and 4 to copy over 4. Right? Dot, dot, dot. Right? 5, 6, 7. At that point, this has been eliminated, and I copy over the last one without making a comparison. How many comparisons did I do there? N minus 1. Is there any difference between these two? N and n minus 1 and n divided by 2. They're both linear functions, right? So let's go ahead and go with the worst case. Right? It doesn't really matter. N minus 1. Okay? So altogether, what do I have? 2 times c of n divided by 2. 2 recursive calls on inputs that have been halved, right? Plus a linear amount of non-recursive work. Right? This is actually a non-linear, non-homogeneous recurrence relation. And be my guest to solve this. We could try, but basically what I'll show you how it would end up. I'm going to lose the forest for the trees really quick here, right? 2 times c sub n divided by 2 plus n minus 1. Right? What you do is you try to eliminate this recursive term by plugging it back into itself. Right? This is equal to 2 times c sub n divided by 2 ends up being divided by 4, right? Plus n divided by 2 minus 1 plus n minus 1. Basically what I'm doing here is I'm unfolding this. Right? I am trying to eliminate this term by plugging it back into itself to get this term. Keep doing that. 2 times. So you can predict what this is going to be. 2 times c of n divided by 8 plus n divided by 4 minus 1. And then don't lose everything else. N divided by 2 minus 1. And then plus n minus 1. Eventually you'll see a pattern forming here. Right? And you'll see that we've got 2, 2, 2. So I've unrolled it 3 times now. Or I've unrolled it once, unrolled it twice. So actually it's going to be 2 to the k plus 1, where k is the number of times I have to unroll it. And then this is going to end up being, c sub of 1 eventually. And then you're going to have a whole summation over here of n plus n divided by 2 plus n divided by 4 plus n divided by 8 plus n divided by 16, right? Dot, dot, dot. Right? Do you actually really want to solve it? If you do, what I would suggest is you use a tool. Right? And I don't know why I got rid of it, but Wolfram Alpha. C sub n is equal to 2 times C sub n plus n minus 1. Now before I hit enter here, what I'm going to do is I'm going to show you another tool, right? So remember that we've got this thing right here, okay? The other tool that I'm going to show you is we don't actually really want to solve this. Computer scientists aren't interested in solving these things. Mathematicians would be. If you take ODEs, ordinary differential equations, eventually, this is basically that, or that you're solving these ordinary differential equations, linear and non-linear, homogeneous and non-homogeneous. But in any case, we don't really care about that because we're not in diffie-q, right? That's what we called it. You call it diffie-q instead of ODEs. Instead, we care about the, where are you, master theorem, right? Now, there are a lot of caveats here. It's not really the master of anything. I don't know why they call it the master theorem because it really only applies in this very, very specific case that seems to pop up all the time with divide and conquer algorithms, though, right? If you have a recurrence of the following form, right? In other words, you are making A, recursive calls, right? And you're cutting the input by a factor of B, right? And you're doing and f of n is the non-recursive work that you're doing, then all you have to do is identify A, B, and D, where D is your f of n bound, think of this as big O, right? In fact, I can go ahead and get rid of that. There we go. Now it's definitely big O. That's theta. Theta is just another tight bound, right? Don't worry about it. All right, but in any case, it's big O of n to the D, right? Then all you have to do is plug and chug. Given A versus B to the D, right? Then it's going to be one of these three cases. If A is strictly less than B to the D, then this is big O of n to the D. If A is equal to B to the D, then this is big O of n to the D log n. If this is greater than B to the D, then it's n to the log base B of A, right? These are just three cases that you end up plugging and chugging. And by the way, I have never seen this case come up in any practical real algorithm. This will come up in other cases where, like matrix multiplication algorithms, I've seen it. And like Fourier transforms and Karatsuba multiplication, so fast multiplication algorithms. This is the one that comes up all the time for us, though. Okay? What is this actually saying over here? This case says that you're doing less recursion, more work, more non-recursive work, because A is the number of recursive calls that you make. And so A being strictly less than B to the D, B to the D is capturing the amount of non-recursive work that you do, because that's how much you cut the function down, and that's how much non-recursive work you're doing with respect to D, right? If A is equal to the B to the D, then you're saying that you're doing an equal amount of recursion and non-recursion work. This says that you're doing more recursion, less work. More recursion, less work. Right? That's the intuition behind it. You don't need to understand the nuances here to apply it, though, because all you need to do is identify A, B, and D. Now let's go back to ours. Right? Is it in that form? Yep. What is my A here? How many recursive calls am I making? 2. How much am I cutting the input in each iteration of my recursion? I'm cutting it in half. So B is 2. Now what about this, D? Right? I need to focus on this f of n. F of n is equal to n minus 1, which is big O of what? Here we don't need a proof at all. Just tell me what it is. It's a linear function, so it's order n. And what is the D there that's hidden? Because I don't write 1 as an exponent ever. D is 1. Right? So 2a versus b to the d. 2 versus 2 to the first. They are equal. And therefore, C sub n, the number, and remember what C sub n is, the number of comparisons by merge sort on an input of size A is going to be order n to the d log n. But you just told me that d was 1. So this ends up being order n log n. Right? What did we call that again? It's not linear, it's not quadratic, it's something in between, quasi-linear. Right? This is the best you can hope to do with sorting algorithms. There is a known lower bound that you can't do better than this. And some people would say, well, wait a second, radix sort, you can do that in linear time. Radix sort is not a comparison-based sorting algorithm. If you've ever heard of radix sort, all you do is, if you have a bunch of numbers, right? 7, 8, 4, 3, 9, 1, 2, 1, 7, 5, 4, 7, right? What you do is you start, or it's kind of a bucket sort or something like that. What you do is you start with the highest order term here, and then you start collecting them. Okay, so this one is the largest because these are implicitly 0 here. You only sort based on a column first. Then you sort on the next column, so I would actually move this one down so that it's 0, 7, 7. Then this would end up being 8 right here, and so I would rearrange those as well, right? Actually, I forget, maybe you go the other direction, but in any case, it looks at columns here, right? It's not actually a comparison-based sorting algorithm because what if I gave you numbers that were billions of digits long, right? Nope. It takes advantage of the fact that the inputs are all a fixed size, so like 32-bit integers, right? Okay. So in any case, I'm telling you that this is optimum. This is the best you can do for comparison-based sorting algorithms. Merge sort, right? One other example here. Have you ever seen quicksort? All right, here's quicksort then. Quicksort. Right? Here's the basic idea. Given, actually, no, let me type it out. My handwriting is atrocious, sorry. Merge sort. So let's look at quicksort. So here's the basic idea. Given an array of n elements, right, you choose a pivot element. Basketball season is now over, but, big NCAA basketball season is over, right? They played. March Madness, March is over, right? So, no basketball fans. I'm not a basketball fan either. NBA is still going though, right? So what is, we know what a pivot is though, right? All right. What is a pivot foot in basketball? Right. It's the foot that you put down and then you can't move without passing it, right? And so you can pivot around it though. You keep your foot down and you can pivot around that point, okay? So with our pivot element, what we're going to do is we're going to partition. We then partition the other elements around the pivot. Right? That is, things less than the pivot will be placed in the left half. Things greater than the pivot will be placed in the right half. Okay? And then what we do is we recurse on each partition, left/right. Let me just go ahead and show you an example. Let's see. So there are lots of ways that you can choose a pivot element. I'm just going to choose the first one. Right? So let me go ahead and go with 7, 1, 2, 9, 8, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. There we go. All right. So my pivot element here is going to be 7. Right? Then I'm going to go through the rest of these, and I'm going to partition around that pivot element. I'm going to put 1 to the left because it's less than 7. 2 will go to the left because it's less than 7. 9 is greater, so it'll go to the right. 8 is greater, so it'll go to the right. 3 is less. I can't believe I did this. 4 and 5. Right? And then 7 ends up being the pivot element right in the middle. Right? It's not supposed to be completely sorted at this point, but that's just because I was not smart enough to make sure that it was jumbled up enough. Right? In any case, let's go. You would end up recursing on the left and the right. Okay. What about 7? Should I ever move that? Everything over here is less than the pivot element, and everything over here is greater than the pivot element, which I'll call P, right? And so we leave it where it needs to be. Okay. I think I've got pseudocode for it. Let's go ahead and check. There it is. Quick sort. There we go. So it's very, very similar to selection sort, except that instead of evenly dividing it, it has this subroutine called partition that partitions everything to the left or right and returns a pivot element here. This is the pivot / index of the pivot element, right? And then it recurses on the left half, it recurses on the right half. Note here that we go with P minus 1 and P plus 1 because we never touch that pivot element again because it's where it needs to be, right? It's right in the middle of everything, okay? So what does the partition pseudocode look like? Hopefully I have it. There it is. Right. There we go. Again, it's overly complicated to actually write this out, but we'll assume that the first element is our pivot element, and then we'll keep track of I and J. And what we do is we look at I and we look at J. We find something that's on the wrong side. Then we find something that's on the wrong other side. Right? And now instead of shoving everything over to the left and shoving everything over to the right, all we do is take these two things that are on the wrong side and swap them around. So now they're both on the right side, the correct side. Right? And then we continue. Find something that's on the wrong side on the left side. Find something that's wrong on the right side. Swap them around until you meet in the middle. And at that point, when you're meeting in the middle, you just have to swap the pivot element and you're done. Right? The elementary operation here is, again, there and there, right? You're comparing an element to the pivot element, right? And then you're doing one more here technically, but we won't worry about that, okay? All right. So let me show you the worst case. Worst case. Right. So 1, 2, 3, 4, 5, 6, 7, and 8. Here's my pivot element, right? What do I end up doing? I make a comparison to everything, and then I split it up how? The left partition is going to be how big? Is there anything less than 1? Nope, it's going to be 0. What about the right partition? How many is it going to have? All of them, all the rest of them, 7, right? So in other words, more generally, I will end up partitioning, if there were n elements here, right? My left partition would end up being 0, and my right partition would end up being n minus 1. Okay? That's for the partitioning. Okay? What about these recursive calls here? So once again, I'm going to set up a recursion. Let C sub n be the number of comparisons, comps, by quicksort on an array of size n. Okay? C sub n, this is the worst case now, remember. We are going to make a recursive call on an empty list, C sub 0. Right? Then we're going to make a recursive call on a list of size n minus 1. Right? Now, how many comparisons did we make to do that? Right? Well, we compared the pivot element to 1, 2, 3, 4, 5, 6, 7, 8, or 7 elements. Excuse me, I lost my count there. Right? So more generally, how many comparisons are we going to end up making? N minus 1. Magic, magic, magic. You solve this and you end up with order n squared. Does that sound quick? No. So let's not look at the worst case. Let's look at the best case. Best case. The best case here is when your pivot element ends up being the one in the middle. What do we call that thing, by the way? If we have a bunch of numbers over here and a bunch of numbers over here, right? And they're roughly n divided by 2 and n divided by 2. And here's my pivot element. Right? We call that the median, exactly. So if our pivot ends up getting lucky and it ends up being the median, then we end up splitting it up into two partitions of equal size. C sub n now is C sub n divided by 2 plus C sub n divided by 2. And that's still that same n minus 1 because we still have to partition it. Does that look familiar? That's exactly the same thing as merge sort, which we already found out was n log n. Right? So which one should we go in this case? Worst case? Okay. That means that you would never actually want to use quicksort despite its name. Best case. It actually turns out that the best case is equal to the average case. In other words, in practice, quicksort is actually quick, right? Because what is the worst case here? Your pivot choice ends up being what? The minimum or the maximum element. How lucky would you be to always choose the minimum? Always choose the minimum. That means that it would have to be sorted. And you can check for that up front before running your algorithm. If it's already sorted, then don't do this, right? And to check that it's already sorted means just n comparisons, or n minus 1 comparisons technically, right? So in the best case and the average case here, you're still going to have order n log n, right? If you want to, of course, you can always go with merge sort, right? Merge sort where we started way over here, and then have a guarantee. That's guaranteed order n log n all the time, right? Okay, so there's quicksort, right? And let's just do a summary of these, right? Remember the ones that we started with, selection sort, right? Terrible. Why? Because it is order n squared, and that is not acceptable. If I'm trying to sort 1 billion things, I'm going to be waiting 20 years to do so, right? What about insertion sort? That was also order n squared, right? But can be better than selection sort in the best case. Right? Because remember the best case, and best case and average case. You end up making, it's adaptive, right? You end up inserting it. You don't always need to compare the element that you're trying to insert to every element before it, right? You only need to compare it to the number of elements before it, and then you can insert it, right? So you might get lucky there. Right? Merge sort is guaranteed to be order n log n. Remember what we called that? Quasi-linear. Right? Quicksort is likely to be order n log n, right? But it can be in the worst case, order n squared, right? There's another one, Tim sort. Have you ever heard of that? So for 20 or so years, Java used a modified merge sort until Tim, I forget what his name is, but his first name was Tim Peters, that's it, developed his own sorting algorithm and added it to the Python language. And he didn't call it Tim sort because nobody's that full of themselves. Instead, since he wrote it, other people started calling it Tim's sorting algorithm, right? Now we got Tim sort out of this. And it's also order n log n. Right? There we go, order n log n. And it's adaptive. Right? So it's kind of like merge sort, but instead of this divide and conquer strategy, what it does is it goes through and tries to find sequences of pre-sorted stuff, right? Because it's not, data is not always going to be random. You're going to have like 50 elements that are already sorted, that are in order already. You're going to have another 20 elements that are in order. You're going to have another 15 elements that are in order. So it finds these sub-chunks that are already in order, and then it uses the merge routine to merge them together, right? Then it takes the next sequence and the other sequence and then merges those together until it all works. In practice, it's very, very fast. In practice, it is very fast. Right? And in fact, this is what Java and Python use this, right? Since some version, right? Older Java used a hybrid algorithm. Right? So what do I mean by hybrid algorithm? Let's come back over here. Oh, we never actually evaluated this. Remember this is the best, this is merge sort and the best case running time of quicksort. Please solve this for me, Wolfram Alpha. And, oh, you're not gonna solve it, are you? Solve? R solve? Recursive solve? No, it's not gonna do it for me. Fine. Anyway, 175 n squared plus 3 n, I think that was it, and then n cubed. Let's go ahead and plot those. And then I'll only plot it from 0 to 100. No, 200, let's go to that. Right? So what is a hybrid algorithm? A hybrid algorithm says, look, I know that n cubed in the worst case is going to be, that this n squared down here, that's going to be the best overall. But for small inputs, this n cubed algorithm, this slower algorithm, does outperform the other one. So we're going to be adaptive about this. If you give me an input size that is greater than this value here, I'll use one algorithm. If you give me an input size smaller than this size, I will use the slower algorithm because I know in practice it's better. Right? And that's exactly what happens in collections.sort. Right? Let's go ahead and take a look at it. Right? Come on, there we go. List.sort, there we go. Arrays.sort. There we go. It's called, well, first of all, of course, if user requests the old one, merge sort over here, it uses that. Otherwise, it will use Timsort, Tim's sorting algorithm. I wonder what that looks like, first of all. It looks like it's, okay, no, I want Timsort sort. There we go. All right. If the array is too small, do a mini Timsort with no merges. And then it matches over the array once, left to right, finding natural runs, like I said, things that are already pre-sorted. Extending so short natural runs to min run elements and merging runs together, stack invariant, blah, 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 right? It's doing some binary sorts, right? And then it merges all remaining runs to complete the sort, right? So it's finding all these runs and then it's merging them together somehow, okay? You can go ahead and take a look at that later if you want. What were they doing before they introduced that, okay? This one, there we go. All right. If the length is below a certain threshold, in other words, if the input size is small enough, we do this thing right here. And the comments tell us that that is insertion sort, the slow sorting algorithm, right? The n squared algorithm right here, but that is good in practice, right? Otherwise, what it does is recursively sorts all those halves, calling itself recursively, there's merge sort, until it gets down to that cutoff point. What does small enough mean for Java? So what is the insertion sort threshold? 7. Right? If you have an array, an input of only 7 elements or fewer, it won't do merge sort. It'll do insertion sort because it's faster, right? Because you're not, you end up paying for the recursion. Function calls, that is expensive in practice, right? And why would you do that for something so small, right? 7, all you need to do is arrange it really quick, right? And so it cuts itself off, and I can go back now, there we go. If it's, or I guess if it's less than, so 6, so 0 through 6, not 7, right? And they probably did a whole bunch of empirical tests to find out, well, what's the optimum cutoff point there, and they decided, okay, in general it's going to be work on small arrays, and small here means 6, or 6 or fewer. Okay. All right, and that is a straight run of insertion sort right there. Right? If you just took our pseudocode that we gave you last week, this would pretty much be it right here. Right? Okay. So that is a hybrid algorithm. The hybrid algorithm is for small inputs. It uses a slow sorting algorithm because the recursion would be more expensive than the savings of recursion, right? For larger inputs, it uses recursion. Right? it uses the recursion that we just talked about, right? For merge sort. Merge sort. There we go. There's one other sorting algorithm that we're eventually going to get to called heap sort, right? Heap sort is a really smart data structure called a heap, right? In fact, it exemplifies the theme of this course. If you remember way back at the beginning, I don't expect you to, but one of the themes of this course is smart data structures and dumb code are a lot better than the other way around, right? Heap sort, when we finally get to it, is going to be 2 lines of code. Put stuff into the heap, take stuff out of the heap. That's it. Right? You put stuff in, you take stuff out. That's dumb code, right? Because it's just two for loops, and that's it. But it's a smart data structure because when you put stuff in, it efficiently stores it. When you take stuff out, it comes out in a sorted order, right? Yeah. And ultimately, it's going to end up being, with our analysis eventually, it's going to end up being order n log n. Right? Log n, there we go. Right. Unfortunately, Java does not use heap sort, but if you take a look at any implementation of C, right, and heap sort, there we go, you will find that there is a standard implementation of heap sort and merge sort and queue sort. All right, and in fact, queue sort is probably what you used in your C programming course last semester. You know, okay. If you didn't use it, well, you might have used it if they'd covered that. But guess what? Guess what the Q stands for, first of all? Quick sort, right? However, it doesn't have to be. Right? Is a function modified partition sort or quick sort? I guess it is for this particular implementation. But I've seen implementations where Q sort is actually just calling heap sort because it has a guaranteed running time and it uses a smart data structure. Right? Except that it's reentrant probably. Thunk, which is past. Can't believe they called it that, but whatever. They're not stable. Heap sort function is implementation based on a variant of heap sort. Okay. And log n, worst case, running time, blah, blah, blah. Right, you can read all about it there, but there is a heap sort, merge sort, quick sort implementations in basic C. Right. Okay. So next time we'll go ahead and start the last module for this course. Last module is going to be trees, right? We have what, 3 weeks after this week? Right, so I don't think that we'll take the entire time, and if we want to cover something special in the last week, let me know. Otherwise, if we want to just take a break for the last week, that's fine with me too. If we want to change class into like a help session for the last week, that's fine. Remember, the only things that you have left are assignment 5, 6, and 7. Right? 5 is your database pull. You're loading data from your database. 6 is going to be your persisting data to your database. We give you a class to do that, and you have to implement all those functions. And then 7 is going to be designing your own sorted list class that maintains an ordering. And I've seen some of you have already designed your stuff in your design document, so you're well ahead on that, right? So let me know what you eventually. It's several weeks away, so don't worry about it yet. But we'll start covering graphs. Trees are a special type of graph on Thursday.